We can see two metallic spheres pushing away from each other without ever touching. But to understand why, we have to look past the spheres. We need to zoom into the empty space around a single positive charge. This source charge changes the nature of the space around it. Scientists call this altered space an electric field. To map the direction of this field, we imagine placing a tiny positive test charge into that space. Because like charges repel, the positive source charge pushes our test charge away in every direction. We represent this movement by drawing field lines pointing outward. If we swap the center for a negative charge, the positive test charge is pulled inward. This is why the field lines for a negative charge point toward the center. These lines don't really exist. They simply show the direction a positive test charge would move if it were placed at that specific spot. When we place two positive source charges close together, the space between them becomes more complex. A test charge placed between them is now being pushed by both sources at once. It's forced to curve away, which is why we see these field lines bend away from each other. Now consider a positive and a negative charge side by side. Based on how a positive test charge moves, try to predict the direction of these field lines. The test charge is pushed away from the positive and pulled toward the negative, creating lines that connect the two charges directly. This same logic applies to two large parallel plates. Because the charges are spread out across these flat surfaces, the push and pull on a test charge become balanced throughout the gap. Because the force is now the same at nearly every position, the field lines become straight, parallel, and equally spaced. This is a uniform electric field. Up to now, we've watched the field push the test charge around. But imagine we fight the field and hold that charge in a fixed position, right next to the positive source. Because the field is trying to push the charge away, it takes effort to keep it here, much like holding a compressed spring. Because of this position, the charge now has a high amount of available potential energy. If we move the charge farther away, the field's push is weaker. It takes less effort to hold it there, meaning the charge has less available potential energy at this new position. By comparing these 2 points, we can measure the difference in potential energy each unit of charge would have. This difference is what we call voltage. If we stop holding the charge, it naturally falls from the high potential point to the low potential point, shedding that stored energy as it moves. So an electric field isn't just a map of pushes and pulls, it's a map of stored energy waiting to be used. We see this energy map in action inside a battery. Chemical reactions act as the external force, physically separating charges and pushing them to opposite ends. This makes the two terminals the high energy and low energy starting points of our system. When we bridge these terminals with a copper wire, the potential difference between the two ends forces an electric field to form right through the length of the wire. This internal field pushes charges through the circuit. As they move from high potential to low potential, they transfer their energy into the devices we use every day. Remember the chain. Charges create fields. Fields dictate potential energy. And the difference in that energy, the voltage, is the pressure that drives our world.